When I proposed this in 1905, I knew it was true, but there was no experimental evidence, and nearly all of the physicists questioned whether this could possibly be true. We have now since discovered a number of experiments which verify what was called time dilation, the slowing of time with motion. For example, in October of 1971, Joseph Hafele and Richard Keating put atomic clocks on airplanes and flew them around the world. And they verified my time dilation predictions to around 10%. In 1976, Robert Weschert and Mark Levine put more accurate atomic clocks, hydrogen maser clocks, on rockets. And they were able to confirm my time dilation prediction to 70 parts per million. In a number of laboratory tests since then, we have verification of time dilation. In 1962 at CERN, it was verified to 2% with the increase in muon lifetimes. Since then, it has been verified in 1992 at Colorado State to under 3 parts per million. So this is crazy, yes? That time slows down with motion. One thing you should know is that global positioning satellites, which tell you your position in your automobile, and aircraft also use it for positioning, provides a continuous verification of Einstein's prediction that time is slowed by motion and, oh, by the way, by gravity, by my prediction. So GPS simply would not work if we did not take into account the slowing of time by motion and by gravity. So time is relative. In my crazy universe is our universe. So what happens to Mama? We forgot about Mama, yes. Mama takes off on her rocket ship and travels to a distant star and returns. Now let us assume her rocket travels at a speed, a uniform speed of 99.5%, the speed of light, 99.5% c, relative to the Earth. This is about 667 million miles per hour. The time slowing factor, again, is the square root of 1 minus v squared, which here is the square root of 1 minus 0.995 squared, which comes out, if you use your calculators, to 0.1. What that says is that time on the rocket runs 10 times slower than time on Earth. Yes, due to its speed, time on the rocket runs 10 times slower than time on the Earth. Now let us compare the ages of the mother and daughter in this experiment. At the start of the trip, daughter Griselda on Earth was 25 years old. The round trip, it turns out, took 30 years to get to the star and 30 years to return. Earth time. So the round trip was 60 years, as Griselda sees it on Earth. So how old is Griselda at the end of that period? 85 years old, yes, thank you. 25 plus 60 is 85, yes. Okay. Do not worry about your mathematical difficulties. I assure you mine are worse. Mama on the rocket, 45 years old. But to her, the rocket trip took only 1/10 of what it took to the Earth people. So it took 6 years. For her, 6 years went by on her rocket trip to the distant star and back. So how old is Mama on the rocket when she returns? 51 years old.
My own grandpa.
Mama Quetsch returns 34 years younger than her own daughter. And we have another...
When she gets on the rocket,
yes.
And she's now on the Earth.
Yes.
How old is she?
51 years old.
That's all, okay.
That's it. And she says hello to Griselda, and Griselda is 85 years old. Yes.
And upon being, when she gets off the rocket and she's now exposed to Earth's gravity and everything, does she instantly age to?
No. That's only science fiction movies. She remains 51 years old.
That was my question.
So she ages again at Earth rate?
Then, once she is returned to Earth, she ages at the same rate as everyone else on Earth. Yes.
So, what about her aging process?
Time itself has slowed down on the rocket by a factor of 10. Assuming everything else is equal, she will only age at 1/10 of people on Earth. Is there another question?
When you were showing the atomic clock with you walking and it going up and down and more diagonal, to us it's slowing down, but to you, it's the same rate whether you're standing still or moving because you're relative to...
Yes, yes, very good point. Thank you. For me, rather than walking, which is a harder thing to understand, imagine I am in a vehicle that is moving. Okay? It's easier, I find it easier to visualize. As I'm moving in this vehicle, from my point of view, I am standing still, and all of you are moving by me in the other direction. So time for me, and how I perceive the light clock, I perceive it ticking and talking normally. You perceive it as slowing down, but I do not because I am at rest relative to the light clock. Okay, let us assume that the trip started in 2015, okay? So, what was the year at the end of the trip? The Dr. Griselda on Earth, what did the Earth calendar say the year is?
2065.
60 plus 15? This mathematics is difficult, yes. Okay, 2075. Now, Mama on the rocket, on the other hand, only 6 years have gone by. So let us imagine that she on the rocket has a clock, very accurate clock, and every 24 hours she takes her calendar and marks off a day, and after 365 days, she turns the calendar to the next year and does that. What does her calendar tell her the year at the end of the trip is?
2021.
15 plus 6 is? 21. Yes, 2021. She owes 54 years of income tax. I love it. Very good. I'm going to use that from now on. Okay. Mama Quetch has traveled 54 years into the future. Do you see it? For her, it should be the year 2021, but when she arrives back on Earth, it's the year 2075. So she has, in effect, traveled into the future. So we talk about time travel all the time, but the fact is, this is an example that is real, based on the real physics and the real measurement. We know that time slows down with motion. Okay. In principle, if you traveled fast enough, this may answer your question. You could arrive back on Earth thousands of years into the future. If you took a round trip from Earth to a very, very distant star, at 99.99999% the speed of light, remember, according to my theory, nothing can travel at the speed of light that has mass. Except perhaps neutrinos. No. We don't know about that one yet. That is very interesting. But the fact is that at 99.99999% the speed of light, what would happen? I'll answer your question in a second. When you return to the Earth, it is the year 2236 years later. You have effectively traveled in 1 year 2,236 years. In principle, there is no limit to this. You can travel for a short amount of time and come back to Earth into the future, a very, very far distance into the future. Yes, you had a question.
I was going to say, what if I loaded Mama's rocket ship with neutrino rocket fuel and she was able to... I'm trying to understand where the paradox is of, well, I'm thinking going into the past and shooting your father.
You sound like you're excited about that thought.
Well, I saw that one night on the Science Channel. Why you can't travel into the past. Certainly with this physics, we don't know of any way to do that. This allows you to travel into the future, but not to go back into the past and change causality, is what they call it. Okay.
Now let's talk about everyday time. Yes, I'm sorry, you had a question.
Can we talk about something before, about things having to go in a uniform direction?
Uniform speed.
So when it turns around to come back,
It's not uniform.
it's not uniform?
Yes. The rocket ship, in fact, doesn't travel completely in uniform speed. It has to turn around and go back, and that makes it non-uniform. And that, by the way, is an acceleration. And that is the reason why the rocket ship time is slower, but not the Earth time. It is that acceleration that is, they call asymmetric, which tells you that it is the rocket trip. Only the rocket ship experienced acceleration, so only the rocket ship has the slowing of time. Okay, everyday time travel. But people don't realize is that we do this all the time. Let's imagine you leave for work in the morning and your roommate, significant other, or whatever politically correct description there is for this person, is in bed sick. And you go to work, you drive to work, you go into the office, and at the end of the day, you come back out of the office and drive home. You return from work in the evening, and because of your emotion to and from work, time has run a tiny bit slower for you. Because of your emotion in your car or any other emotion you had during the day, compared to your roommate who is lying still in bed, time has run a tiny, tiny bit slower for you. This roommate looks like he's even sicker, yes? Okay. So the point is, because you have had your time run slower than your roommates, when you arrive back at the roommate, you have effectively traveled a tiny, tiny bit into the future. So every time you travel and you come back to where you started, you come back a tiny bit into the future, because your time is run slower than time where you have left. So you are always time traveling. It's just such a small effect, billions and billions of seconds, that we don't notice it, but it is real. So, it's supposed to be a drum roll. We are all time travelers. For more information, you may go to my website, marxmodernphysics.com, and I thank you very much for your attention.